Okay, time has come. Good morning, everyone. All right, let's get serious. I'm here to talk about some things that may well determine the fate of humankind. These things include machine learning, a machine learning library from Google called Tensorflow, and my recent efforts to bring Tensorflow to Clojure. All right, I already did that. Nice. All right, first a bit about myself. My name's Piel. I live in the Philadelphia area. I work at Magento on their business intelligence offering, and I can get pretty excited about programming. Oh yeah, I'm going to say ML sometimes because I get tired saying machine learning so many times. I'm also going to use the word idiomatic too often. Okay, so there's quite a few talks about machine learning at Cons this year, and I'm very happy about that. Raise your hand if you saw Joyce's on Cortex yesterday? That's really good. That's good. Because she did a great job explaining things that maybe I am not going to do a great job with, but you know, she filled in the gaps. That's good. Also, I believe Will Hoyt from Yet Analytics is talking about deep learning for J tomorrow. I would see that one too if I were you. And Karen Meyer is talking about some ML deep learning things. Go to all those. Okay, so why am I so happy about this? I'm very confident that machine learning, deep learning are going to have an increasingly profound effect on the landscape of software development in the coming years. And well, look at this food chain. This guy tweeted this picture, I really liked it. Machine learning is big, and it's getting bigger, and Clojure needs to be in the game. I would love for ML to be like a big growth opportunity for the language that we take full advantage of. And despite the topic of my talk, I don't particularly care about which tool gets us there. I would be ecstatic for any of these to bring Clojure to the front of the field of machine learning. I think TensorFlow might be a good option for us, but other tools such as Cortex and DL4J, which are being presented, as I said, I really don't know that much about them, so they might be great too, or better. Do I have anything else to say about this? So my allegiance here is really to Clojure. That's my point. And if you feel similarly, you have to ask yourself, what do you want the future to look like? This unfortunate scenario? Or this? That's probably Elon down there. Sorry. But Python's fine, I guess. I have some good friends that use Python. It's not Clojure. I don't know. So, for my part, earlier this year, I was taking a deep learning class online, and I guess things got like a little bit out of hand because I'm excited to tell you that I wrote a TensorFlow library for Clojure. It attempts to deliver TensorFlow to Clojure in like a very idiomatic way that enables the kind of like rapid iterative development that we all love using in Clojure already. So I call this thing Guildsman. What is TensorFlow? TensorFlow, if you don't know, is an open source machine learning library. It was released in November 2015 by Google, and it was like mid-2016 that it got CAPI bindings, which allow other languages, like Clojure, to be able to leverage the core of TensorFlow. It was a few months later that Java bindings were introduced. TensorFlow works by exposing an API that lets you build, execute, and inspect a graph of nodes. Each node applies some operation to one or more tensors, and of course, like the tensors flow. if that wasn't obvious. Conceptually, this is not so different from like how data gets passed from function to function in typical software, so don't be scared. All right. When I applied to give this talk, a few months ago, Guildsman was in like a bit of a mess. It was a rough state, but it was moving along very quickly, so I felt confident. And I indicated in my proposal that like things would be all cleaned up and presentable to the public by the time of the conference. I did not really keep that promise. I'm sorry, Alex. So instead of that, what I did do, instead of that, or trying to pursue like feature parity with the Python client, I decided to focus on demonstrating like the potential that I saw in Guildsman, and more generally the potential I see for doing machine learning in Clojure. But, like this crazy car, Guildsman does work, and we will see some live demos to prove that. This has already come up in a few conversations that I've had since the conference started, which is that there's this strange situation where TensorFlow is like a giant in the field, it's relatively mature, you can do all sorts of things with it. And then there's Guildsman, which I only started working on a few months ago. What functionality can Guildsman, like what functionality of TensorFlow does Guildsman actually expose? And the answer is like not all of it. It's not totally intuitive either, like what stuff does get exposed and what doesn't and why. I'm going to try to get into that. I'm going to try to give a good explanation of that because I want you to get kind of like the full context of where this thing stands. So this is the architecture diagram on the TensorFlow site. It has a lot of details that are not important to us right now. Here's my simplification. This is better. So note the C API, that blue guy. That's important for a couple reasons. The TensorFlow core beneath the C API is written in C++. And that's great because C++ is reusable by Clojure. Python's not. And also, Python is, slowish compared to like C++. C++ is fast. That's where TensorFlow gets its speed. So I like that C API. I like how it spans like the entire horizontal space. That's a nice clean separation, right? Is this rounded rectangle real, though? Does this represent reality? It turns out this is more of a plan than how things actually are laid out right now. But in the early, naive days of Guildsman, I believed in this fantasy. What the functional? Python has access to this kind of cheater API that allows things that to be possible that are not available to the C API that the rest of us are forced to use. Now, rest assured, the Google TensorFlow team is hard at work porting functionality, improving the C API and porting Python over to using the C API. So everyone's going to be on a level playing field. So maybe that's okay. Oh. Turns out there was a lot more Python than I expected when I started this project. So this makes the prospect of achieving feature parity between the Python client and Guildsman somewhat of a daunting task. I persisted despite this revelation because I felt like I could achieve some sort of like 80-20 Pareto portion of functionality that would still make Guildsman worthwhile. Okay, so while we're talking about architecture, TensorFlow does ship with a slim, relative to the Python offering, a very slim Java implementation. The two green layers are the ones that are specific to Java. The C++ layer, note those letters J and I next to them. This stands for Java Native Interface, and that allows the JVM to leverage native libraries, and in this case, gets us access to the C API. Some other people earlier this year have published examples of using TensorFlow in Clojure, and they've done so by just leveraging Java interop with these provided classes. That's a sane approach, but not the one I took. You know me. So here's what I did. Here's the Guildsman stack. The green layers, again, are ones that I implemented myself. The big difference here is that the Java classes that I implemented are even slimmer. They're stateless, they're minimal. They do very little more than, they don't do much more than just act as like J and I bindings. So that brings Clojure as close as possible to the underlying CAPI and the TensorFlow core, and I think just serves as a much better foundation for everything else that I did. Okay. So I'm going to talk a little bit more about the design of Guildsman, but first I wanted to get concrete for a minute. I put together a Hello World example that's just adding two numbers together. For fun, I did them both in Python and in Guildsman, and made both as simple as I possibly could. Here's the Python. I guess that's okay. Like, it seems like a lot of typing just to add two numbers together. We have a graph that's instantiated for us. You can't see that, but it exists. It's used implicitly, but we still have to instantiate a session, define the scope for it being used. That's better. This is the Guildsman code. Details like the graph and the session are completely incidental for a case as simple as this. So in Guildsman, you're not forced to touch them. Another big difference between Python and Guildsman, and like a critical design issue, is that in Python, you start by building the graph. All the node building logic needs to have access to that graph instance, which means it needs to exist first. It needs to exist locally on the same machine. It also means that any function that builds nodes necessarily has side effects. We don't like that. Upon understanding all this, I had an immediate visceral reaction, and I knew that any kind of idiomatic TensorFlow library for Clojure could not work this way. So here's what I did. In Guildsman, you start by creating a plan. And a plan is a data structure. It's in the shape of like nested maps. Each node is defined by a map and contains the definitions of other nodes that it takes inputs from. For example, you can call a planning function and get a map like this one. So add represents the TensorFlow's add function. And what we get back is, yeah, this pretty simple map. There's not too much going on. It's not scary. And this approach affords us the benefits of data-oriented programming that we all know and love. Now, at this point, I wish that Rich could just like appear here, say something really eloquent, blow our minds, and we'd be done with this slide. But instead, you have to settle for me. And my thoughts on this are that there's a few different benefits. Like, first of all, data can be inspected directly. You can look at these plans. So when you call a planning function, you know what it's doing because you can look at the map that's being returned. It's not the results aren't being like hidden away in TensorFlow or some Java object or something like that. And as a result, yeah, you don't need any side effects. Also, composing data is a lot easier. The composing logic, when you're composing plans, can be more easily decoupled from the functions that are providing those inputs. Plans are reusable across graphs. They can be stored or transmitted maybe to like another server for execution, maybe one that has a GPU. You get deduplication for free. In Python, if you create two sets of nodes that are identical, you have the cost of that redundancy. Guildsman can tell that two node plans are identical and just deduplicates them for you. No big deal. Finally, the node planning logic does not need to have access to a graph instance. And I think this is good because a TensorFlow graph is append only, which is a nice feature, but it's still stateful. You do not want to be touching it more than you have to. In total, I think the separation of the planning and building phases is probably like the most impactful design decision that I made with Guildsman, and it's what allows Guildsman to deliver like an idiomatic experience. Okay, so adding two numbers together is great, but let's get on with learning, and we'll do something slightly more advanced, but not too crazy. We are going to look at this expression. And if you do some math, you'll see that the lowest possible value for this expression is 0. And you arrive at that point when x equals 2. This is the absolute value of x minus 2, if that wasn't clear. So you arrive there when x equals 2, but we're not going to tell the machine that. It's going to have to learn it on its own. So here's the code that you can use to represent that equation in Guildsman. We start off by instantiating a variable. Variable's name is x. We initialize it to a value of 0. This is the only stateful part of our graph, and it represents the current state of like what we've learned and the solution to our problem. We subtract 2 and take the absolute value. So that's the end of planning. We have yet to actually touch TensorFlow, and it has no idea what's coming. We feed that into build session, and that's when the build phase begins. So this is going to take our plan, feed it to TensorFlow to instantiate a graph, and from there start a session. All graph execution takes place inside of the context of a session. There's a function run global vars init that initializes our variables, which in this case is just x. Variable state also exists only in the context of a session. So usually do that right after you instantiate one, and so we're doing that. And finally, we feed our session and the plan for x to produce. This is when the graph gets executed. Now, all we're doing is we're producing the value of x. None of the rest of the equation is getting involved yet, and we haven't done anything to change the state of x, so it returns 0. Nothing too exciting yet. It's time to learn. But how do we do that? The magnitude of error in machine learning is represented by what's called the loss function, as in if it's too high, you're a loser. All right, that worked. That's good. In our case, the loss function is the absolute value of x minus 2. Our learning logic seeks to reduce the value of the loss function, and if that value is going down, it thinks we're learning. These are the tools that TensorFlow gives you in order to support the education of machines. I put them in an order that makes sense to me, where gradient descent is the highest because it's the one that developers interact with most directly. I'm going to go through these as quickly as I can, try to give you some kind of sense of what they are if you don't already have one. Gradient descent is often represented by pretty pictures like this one. The altitude at any given point represents the value of the loss function, and our graph is essentially dropped in some random place in this beautiful rainbow hillscape. Gradient descent is the iterative process of trying to find the lowest point by taking steps in the direction of steepest descent. This is similar to how like a ball would roll down a hill. That's maybe not like a perfect model, but it's actually a pretty solid conceptual foundation, I think. All right, so I'm going to helpfully read these to you. Gradient descent attempts to find the lowest value of the loss function. It steps in this direction of steepest descent to do so. Backpropagation calculates the slope of the loss function and is a special case of automatic differentiation. Automatic differentiation reduces our loss function to atomic operations, takes the derivative of each, and combines them using the chain rule. You remember the chain rule from calc class? This is the only application of it, I think. All right, so here's my attempt to just kind of get all this information, boil it down into the relationships and their simplest elements. But the key thing here is what's at the top and what's at the bottom. In order to do machine learning in TensorFlow, you have to have gradient implementations, meaning you have a graph, it's got nodes. If any of those nodes use an operation that doesn't have a corresponding gradient implementation, then that node cannot participate in learning, which is a big deal. See? So this is actually one of the larger obstacles towards achieving, in the quest towards achieving feature parity between Python and Guildsman. Python has all of its own gradient implementations, the TensorFlow Python client. TensorFlow also has a bunch of implementations in C++, and that's great because those are reusable in Clojure or any other language that's using the C API. Guildsman also has some of its own written in Clojure. Why is that? During the course of development, I learned things, and there was flipping and flopping, and so now there's both. This is not a terrible scenario to be in, though, because the C++ gradients have been giving me trouble where sometimes my JVM crashes, and I'm not sure whose fault that is yet, mine or Google's, but could go either way. The Clojure ones work consistently, so that's what I'm relying upon in order to not be embarrassed during this presentation. So maybe it's a large obstacle, but it's not insurmountable. I had not written any C++ since around the time that I learned about the chain rule. But despite that, I was able to knock out some of these gradients without too much trouble. It's not so bad because the mathematical logic, which can be scary, is already laid out in Python for you, and you just need to port that over to C++. So if you're comfortable with those two languages, it's not so bad. And I definitely will tackle more of these as I need them. So if you are interested in TensorFlow or helping Guildsman progress, implementing gradients in C++ for TensorFlow is not a bad way to go. All right, so here's the code that we had. Here it is with gradient descent introduced. Now notice the two highlighted expressions. The first one adds our gradient descent node. We're naming it opt. We set an alpha value of 0.5. That's the size of the steps that you take. And we're optimizing our loss function. The second highlighted expression runs that optimizer 4 times. 4 times is not that many times. You can't usually learn anything with 4 iterations, but our case is so simple that it'll work fine. Whoa, look at that. So this, right? This is the resulting graph now that is produced from our code. That giant red-gray box came from automatic differentiation. So that. What? Oh, no. Look, there's like a few tiny little things at the bottom. That's the original thing. And then the rest, that's what I'm saying, it's big. Gradients are a big deal. Thanks, Mike. Okay, I promised live presentation, or live demo. Here it is. So here's the code I just showed you. It's in my editor. I'm going to run it. 2. 2 is the right answer. So this machine has learned. I'm glad you guys were happy about that, because I felt like that was actually pretty anticlimactic. But I needed to get the liveness out of the way so we can proceed. TensorFlow development is one of those tricky scenarios where the values flowing through your program are not easily accessible. Like, you can't sprinkle prints and defs around to capture those tensors flowing through your graph. And even Saeed is not going to help you now. That's why additional tooling is critical. So Google's solution is a web application called Tensor Board. It's pretty slick. It's got a lot of cool visualizations, and the graph interaction UI is especially cool. And you have full access to this when you're using Guildsman, so that's good. Here's a few screenshots. These are scalar values that have been captured over time. Oh, the way, I should say, the way this works is that while a graph is executing, TensorFlow can capture values from any nodes that you've specified, write them to the file system, the Tensor Board server picks those up, pushes them to the browser for you to look at. So yeah, some scalars over time. We can see things look good. Look at this. These are histogram time series, and I find these to be equally like beautiful, useful, and confusing. There's definitely, I think it takes some time to get used to interpreting these. I'm still coming up the learning curve. This is nice. This is like a many-dimensional data set projected onto 2 dimensions for easy consumption by humans. At this point, the plan was to quickly show you how like that graph visualization works, the interactive graph visualization. No. I left it to the last minute last night to get TensorFlow installed, and I don't know if this is just like a personal problem of mine, but I've been using Python like lightly for years, and the package management, like I don't get it. Nothing ever works the way it's supposed to for me. You run stuff and it's like, oh, Python 2 or 3, and then you're in some sort of like a virtual environment, and like I don't know if I needed like an Oculus Rift in order to figure this out, but I don't know. Python. Let's talk about Clojure. This slide attempts to explain what, to me, is like the most important feature of Clojure. This is the thing that's like, it's so beautiful you can't even look at it without like special glasses. And that is a big deal to me. Like I kind of see this as a core design tenet. And yeah, if you're familiar, I'll plug it like one more time. If you're familiar with my debugging development tool that I wrote called Saeed, the sole driving force of that project was my pursuit of tight feedback loops. I always have that principle like front of mind, and I did so with Guildsman as well. I'll read this quote to try to make it sound as exciting as possible. Russell Stewart, AI researcher, says at Stanford, the chance that you've introduced a bug when coding up a network from scratch is so high you'll want to go into a special early debugging mode before waiting on high iteration counts. The name of the game here is to reduce the scope of the problem over and over again until you have a network that trains in less than 2,000 iterations. Here's what I think about that. So training a neural network can take a long time. It can take hours or days. And with cycles that long, Clojure's like rapid iterative development capabilities like aren't really going to make a dent. But early on, you can strict your problem in such a way that cycles are much shorter. And now it's Clojure's time to shine. So I guess Google's pretty good at web applications, but you know, I've got some strong feelings about development and debugging tools, and I had to make my own. I needed to explore Clojure's potential to deliver rapid, iterative development to TensorFlow. Have I said that enough? So, as quickly as possible, I'm going to run through some live demonstrations. We'll be attempting to solve a classic problem in ML, which is recognition of handwritten characters, handwritten digits. The MNIST data set has tens of thousands of such images. They are 28 by 28 and grayscale. So the idea here is that we're going to start with a very simple network and then see how Guildsman helps us easily iterate to something more complex that hopefully works better too. To the code. Okay. All right. Okay. So here's our first iteration. We'll walk through this line by line. all the action here is going on in this def workspace expression. And def workspace is a macro that I put into Guildsman that attempts to serve as a focal point for all the behavior that you would need in order to develop and deploy a ML algorithm and model. It does not do all that, but it does do some things. Especially, it pushes data to the Gils Web App. But this is like, I'd say this is a key piece of my rapid iteration strategy. So first we define these two values. When you're evaluating an ML model, you train it with a training set, and then you test its predictive capabilities against a test set. And that's how you get you try to get an unbiased number about how well this is actually performing. This is a pretty wacky macro that I developed for good reason. It does a bunch of things for us, but let's just call it a threading macro that gives you access to intermediate values as well as the final value. And here we are, we're calling some planning functions. We've got a placeholder, this is where our image input goes. We've got a dense layer, which I'll talk about in a minute. This is where the magic happens. Argmax, which that's what outputs, it takes the output from the dense layer and tells you which value is being predicted, like the number 8. And again, here's the labels. Labels are the correct values. So here's an image of 8, predict an 8, for example. And then there's a few functions here related to defining, finishing off our loss function, implementing gradient descent. And very importantly, there's an accuracy node. That's going to give us a percentage of how many predictions were correct, and that's what we're going to look at. The accuracy that we achieve with the test data set is what we're going to look at to figure out if we are progressing or not. So here we are building those plans. These are the nodes that we're going to be capturing summary values of as we do training. Here's the data sets we're training in. We're going to go through 100 iterations or epochs. And then every 10th step, we're going to log those summary values. And then we have our test data set, which we feed in also. OK. All right. So here's the Guildsman Web App. Not impressive yet. But we'll run this. What happened? Oh, look at all this stuff. So this is the Guildsman Web App. And it is not as slick as Tensor Board, but it does some cool stuff. For example, because what I didn't like about Tensor Board is that it does all these cool visualizations, but then it divides them out into tabs based on which plugin is providing those visualizations. And I just felt like that was kind of an unnecessary impediment to enlightenment. Instead, Guildsman focuses on delivering rapid feedback. So you click on some node, like this already clicked on this for us, you get all these pretty charts. Last year at Conj, Jason Guildsman presented his awesome proto-REPL, and it went over very well, and I thought, I see, people like pretty pictures. I'm going to give them pretty pictures. So here's your pretty pictures. So look at all these things. So what should we talk about? Oh, here's the simple one is we have our accuracy value. Make it big. So here we can see in the end, for our training set, we achieved total accuracy. Great, except we only got 68% correct in the test set, so that's not so great. Maybe we can, what's next? Oh, I promised I'd tell you, talk about the dense layer. I'm gonna skip it. Sorry. I'd rather show you cool stuff. Okay, so what did we do here? Something that is important in neural networks is to pre-process your data. You want it zero-centered, and you want it normalized, ideally. So you can see here that, let's see our data. Uh-oh, that's not zero-centered. All the data is all the way on the left, which is 0, but then it's hard to see. But the rest of the data is kind of like spread out just in positive numbers, not zero-centered. So what are we going to do? Let's zero-center it. So what I did was I did some pre-processing. I took all of our images, took the mean value of each pixel, and then am subtracting that from each image. Subtraction gets added in right here. And now that we've made things more palatable to our neural network, things should go a little bit smoother. So what did we get this time? Oh wait, yeah, here we go. So here is the data. This was the data before being processed. This was the data after being processed. Oh man, don't worry about that. I guess I'm not capturing that. What you would see is that we'd be able to see that once it was processed, the mean of that data set was now 0, and it's got values on either side of it. Let's look at the accuracy. Do we do any better? Oh, this thing is real. See, I told you this thing needed work, because it's definitely blowing up on me right now at the worst possible time. Here we go. All right, so here's our accuracy. So this is unfortunate, and the problem with practicing this talk is you never know exactly what's going to happen, but we actually did worse. I'm gonna go ahead and blame everything that goes wrong on the fact that we've got to do this whole process in a very compressed time. I think if we were using like larger data sets, like more realistic development scenarios, that these tried and true techniques would actually always yield benefits. But for now, I'm just going to wave hands and make excuses. Let's go straight to something cool. Nope, sorry. We're gonna go straight to the big guns, which is convolutional neural networks, or CNNs. There's two key components there. There's the convolutional layer, which does this. It has one or more learnable filters, and they're smaller than the image, but it slides them across, applying them at each step to get this new layer. And this kind of gives the layer a sense of like spatial locality awareness. Here's cool. This is cool. Here's examples of like a 3-layer CNN that's been trained on faces. You can see like each successive layer learns more and more complex traits of faces. So I think this gives you like this can give you like a pretty intuitive feel of what's going on in this crazy CNN. The other important layer in a CNN is the a pooling layer. In this case, we're taking this square, applying it to 4 different regions, and just taking the maximum value in each of those. All right. I guess if you want to see like the whole demonstration, you gotta like, I don't know, track me down somewhere. Okay. So, whoa, that's much bigger. And here's what's cool. As the training is going on, this thing is updating in real time for us. So we can see like, all right, here's where we stand. We're getting up to 83% accuracy for the training, but our test accuracy is still very low, but it's climbing. That's great. Now, in the future, I want to make it so that if you see things have gone like way off the rails, you could just stop this process, and that could save you a lot of time. Another interesting thing that happens is that the loss can go up the accuracy can go up and down. So it's not necessarily like a progressive thing that happens where you're always getting smarter. I am officially out of time. I will close by saying that I had a lot more great content. And that I hope to have a very usable alpha out before the end of the year. I hope I've, even with a subset of my content, inspired enough excitement that somebody's going to try this thing out once it's ready. And enjoy the rest of the conference.